in terms of mathematical education techniques, there's a problem which is common across the whole spectrum of education in mathematics, and that is students want to know, why do I have to know this? Or a topic may be, why do mathematicians care about this question? And most particularly in my situation, I'm educating engineers, and they tend to say, "Can just teach me how to solve the problem. Don't tell me all the things that all the fascinating things about solutions when you don't even know what they are." And there's sort of a reserved attitude on engineers' part towards pure mathematics. And this is an event that happened a few years before I was born, 1935. Tychonoff discovered a certain problem had more solutions than we thought, and the problem was very practical. And I wanted to kind of go into it because some work has been done on it lately, and we can just musing about it, I think, can engage engineering students into why mathematicians ask the questions that they do. The problem is a heat rod, a rod that conducts heat. It's cylindrical, it's insulated on the outside, and its two ends are controlled either by controlling the temperature. Let's say we'll hold it at 0 degrees, so I have a Kelvin, or we can put insulation on the end of it, or we can put a combination of having leaky insulation. This is a classic problem in partial differential equations, and one of the first ones you solve. Separations of variables give us a very explicit solution. The most important thing I want to emphasize at this point is that this is the only solution this system has. This is a unique solution. You can prove it mathematically, and if you think about it physically, you've got this rod, it starts off and you specify the initial temperature, you specify what's happening at the two endpoints, and it's insulated on the sides. There's nothing it can do but one thing. There's only one solution. You've sealed it off. You've gotten all the physics specified. Now, we're going to look at the problem where we extend the rod to infinity. So it's an infinitely long rod. Of course, it's an idealization. Since the ends are at infinity, there is no way of specifying the temperature or the insulation. You have no control over that. But this is a natural extension of the problem. It's an idealization which is useful and is used all the time. And Tychonoff in 1935 looked at this problem for the situation where the initial temperature is 0, and none of these conditions matter anymore because the ends are held at infinity. And is this solution unique? And he found, no, the solution is not unique. He found the solution should be 0 for all time. It starts off at 0, nothing can get in or out. And Tychonoff found that, no, there's a solution which is 0 initially and actually proceeds to have certain properties that we looked at later. So we got the problem wrong in a way. Our expectations were not what they thought they were. And I think this is the essence of my talk. This is intriguing why this happens. Now, if you take the finite rod and have its boundary conditions specified and let the length of the rod go to infinity, take the known unique solution, let it go to infinity, then we know what that limiting solution is. It's the Poisson solution. It was known for 100 years before Tychonoff did his solution. And it says if the initial temperature is 0, the temperature is always going to be 0. It's not going to spontaneously generate heat. And so there's a problem here, a question, what is the relationship between these two ideas? The difference between the Tychonov's solution and the Poisson solution. Now, only recently, 2017, has anyone actually tried to compute to some degree of accuracy the Tychonov's solution. This is what Dr. Rodland came up with, and I'm going to show you a map of the temperature for the infinite rod, starting at 0 degrees. So the temperature initially is 0, and this is a very hard computation to make because the scale of the number varies so badly. And so you will see that the times he was able to come up with solution are not as closely matched as you might. But after 1/6 of, let's call it a second, whatever the time unit happens to be, after 1/6 of a second, we see that a solution has appeared. And it's kind of surprising. It's 140 degrees in these units after 1/6 of a second. And a little later, 1/5 of a second, the computed solution has dropped down to 35 degrees. Another feature of the computed solution is this negative. These are Kelvin temperatures, the absolute temperatures. There is an absolute 0. There's no physical meaning to a negative temperature. And just tracing this on a little bit, after 1/4 of a second, it has gone down somewhat more, but still retains these strange qualities. 1/3 of a second, 1/2 of a second. We see it kind of dying out. And Dr. Rodland actually put all these together on one graph. I had to separate them for the purposes of my talk. But so what has happened here is you have the rod, if it's infinitely long, just spontaneously receives a huge amount of heat distributed along, and this is quite different from what the limiting case of finite rods becoming infinite length. Where does this fit into the overall scheme of things? This, I think, would be a question that would intrigue engineers who are sort of challenging why mathematicians ask the questions they do. Some points here is the solution isn't 0. So the understanding of what happened at the boundary when we let it go to infinity is not reliable. And also the solution is not unique. And now here's where it would really make a difference to an engineer. You've been turning in these solutions. I've done heat transfer consulting myself. I've been turning in these solutions, getting paid money for it. Am I going to have to return that money because there's more solutions than the one that I propose? And what is the footing of the Poisson formula? Again, we use the formula. We're going to have to return the consulting fees. Well, you can dismiss this example in the sense that it applies only to infinite rods, which are non-physical. And mathematicians now would ask, well, are there any other further restrictions that could be imposed that make the solution unique? And work has been done here. I'll tell you about that. And then here's the equation, which looks very much like the heat equation. It has a second time derivative rather than the first time derivative. This is the equation for voltage in a one-dimensional situation like a rod. And for an infinite electromagnetic solution, the 0 initial condition is remains 0. You do get uniqueness for the wave equation. Why do we get it for the wave equation and not for the heat equation? So here's some answers or non-answers in some case. Our physical understanding of the boundary conditions is not reliable. I think that's a valid point. Are we going to have to return our consulting fees, or can we dismiss it because it only applies to infinite rods? What is the footing of the Poisson formula? Are we going to have to return our consulting fees? Well, we have an answer here. The Poisson formula looks at the limit of finite rods, which have unique solutions as you let the length of the rod go to infinity. The Tychonov's solution is not the limit of any such situation. It is just taking the plain old equations and applying it to an infinite situation, and this solution suddenly appears. And then what further conditions could be imposed to render the solution unique? Tykhanov himself had some answers, and that's it. If you could insist that the solution stays below an e to the x squared type of umbrella, if you could insist that that happens, then the solution is unique. In other words, any solution which is non-zero would have to be at some point in time exceed the Tykhanov umbrella. And this was improved a few years later, 1995, by Chung and Kip, who raised the umbrella to have actually asymptotically infinite height at time zero. If you live below, if you can insist that you live below this umbrella, the solution is unique. Witter in 1945 said, no, another condition you could impose to make sure the solution is unique is to insist that the temperature be positive. You can't have the non-negative temperatures. That makes the solution unique. But that raises the questions as why did we not need to make that assumption about finite rods? And where in mathematics is a positive in partial differential equations, there's a condition that the temperature be non-negative. Non-negative temperatures are imposed because at 0 degrees, there is no kinetic energy of the molecules. None of that comes into play when you look at the derivation of the heat equation. And now, why doesn't non-uniqueness occur for the electromagnetic equation? And I've got 3 comments here, one serious, one speculative, and one a little insane. The scholarly answer is, well, you have first order time derivative for the heat equation, second order time derivative for the wave equation, electromagnetic equation. You could look at this as a pseudo differential equation and look at different derivatives of order between 1 and 2. There's got to be one cutoff point where the solution stops having the uniqueness property. What is the value, and is that interesting? And then I've seen this in some books written by mathematicians as another answer. It is known that the wave fronts for electromagnetic waves, of course, they move the speed of light. They're finite. Wave fronts for the heat equation propagate at infinite speed because of the imperfectness of the model. So the Tykhanov solution, in either case, maybe sits out there at infinity, and then when at t equals 0, it suddenly rushes in. If it's the heat equation, it rushes in from infinity instantaneously, and you see the Rodinoff solution that I showed you before. For the wave equation, anything that's out of infinity can only propagate in at finite speed. Well, if it's infinitely far away, it's not going to get any place finite at any time. That's not totally satisfactory solution. But another thing is, just playing science fiction a little bit, we can't build an infinitely long heat rod as a material object, and there's just not a finite amount of material in the universe. There's not an unlimited amount of material in the universe. The universe has a finite amount of matter, so we can never build this thing and observe the solution. However, we do build infinite wave conductors. Whenever we turn a light switch on, we radiate heat to infinity. So there's a very basic difference between the two. So my thesis here that I'm promoting is that we have an issue now which actually does make physical sense to engineers. It is a question we have trouble answering. It's the kind of question that only a mathematician would ask, but it's the kind of question that could make a difference to engineers' pocketbooks if we took it seriously. Okay, thank you very much.